Okay, all right, let's get started. So before we start with the lecture, I guess, any feedback from the midterm? I haven't graded it yet, but any feedback on the format, on the length? Because the final will be similar, right? So if you don't, you have issues, you don't complain now, then you have a very similar looking final.
The test felt good for me.
Okay.
I thought the test felt very similar to the homework in length and content, so it was familiar.
Okay, all right. So then if there are no issues, then the final will be very similar to the midterm. Right? Basically, so there's a final exams, 2 hours time window, but I guess it's easier to do this sort of take home, 24-hour, 48-hour test, and then have you submit. Oh yeah, so it wouldn't be like this, which is 2 hours. So this is design, so we have 2 days, so design a bit longer, right? So it'll be too much if it's just 2 hours. Right, so but since in the final what we'll do is there'll be more programming, basically as the course goes on, as we go on in this course. So that'll be, final will be similar format. You can take it home, do it over 2 days and return. Okay. So I'll grade it. I haven't started yet. I'll probably, hopefully finish this week. I'll hopefully finish grading it this week. As for the grades, in general for this course, I think the average for this course tends to be always, fairly high, and I expect to be the same this quarter. Okay, so the average for this course, comes out to be around 3.6, 3.7. That'll be the same this quarter. Okay, so I don't expect people to have any problem with the, with your GPA at the end of the day. Okay, so now any feedback, of course, with the midterm, let me know, right? So either in class or through email or through office hours. Right, so so take home is always a little bit weird, right? So I thought the questions from email was also good, right? In the future, in the final, for example, if you have questions, definitely ask through email, right? So if even if you think your question is maybe getting a little bit too close to asking me to tell you the answer, it doesn't hurt to ask. Right, if I can't tell you, I just say I can't tell you. But I thought, for many people, the questions you have were reasonable for clarification for the midterm. Okay, so right, so there's no issue with that. Then the final will be similar, right? Some similar format to the midterm. Okay. So then let's continue from last time. So let's recap a little bit where we left off, right? So where we left off was basically the Newton-Raphson algorithm, right? So where we ended off with, we're looking at this. So we're looking at this sort of Newton-Raphson algorithm. Right, so it's not a hard algorithm, right? Just a little bit reminder for us as basically it's a loop. I'm gonna loop until the mismatch are small. Okay, so we're gonna loop until the mismatches, until they're small. If they're not small, what we do is we basically compute the Jacobian matrix J. And since we're doing this by computer, we're gonna just invert the matrix, right? So for all the questions you will see, as you can directly just invert the matrix. They're designed to be invertible, basically. The numbers are designed such that you don't run into problems when you invert the matrix. They're gonna compute J, gonna compute J inverse, and then the update will be just delta theta, delta V, K plus 1 is minus J inverse of the current power flow equations. And then what we have is we'll update the K plus 1 terms to be the case term plus basically the changes Okay, so this is the Newton-Raphson method. And once you get all the data set up, get the model set up, it will be fairly quick once you start to run this. Okay? It will converge fairly quickly. Again, so a little bit reminder what J looks like. J is a power flow Jacobian. And J basically looks like something like dp d theta, dp dv, dq d theta, dq dv, right? So this is what the power flow Jacobian looks like. And last time in class, we went through sort of how do we do all this partial derivatives. Okay? And so this is the J, this is the Jacobian matrix for PQ buses. Right? So this basically assuming that all the buses in the system are load buses. And once you take a Jacobian, it becomes just taking partial derivatives with respect to a V and theta for P and Q. So it's fairly simple. It's fairly simple, but it takes a lot of notations, basically to write out all the terms. But none of this derivative is all that hard to do. Right, so this class basically will just look at the PV bus. Okay, so remember, PQ buses, these are loads. Right, so we said for a load, if you're constant power load, you fix your P and Q, and we have determined V and theta. So this class will briefly look at what happens to generator buses. Okay, so this class will look at PV buses. These are basically generators. After that, we'll look at a test system. Okay, so from this week on forward, when you do your homework, we'll be getting into some programming stuff. And the way for it to work is we'll have a particular test system we'll use just to standardize the result we'll have. And we'll work through that test system. Okay, we'll just work through that and throughout the rest of the course. Okay, so we'll be building up and through the programming, we'll look at solving part, we'll look at through building the Y matrix, the J Jacobian matrix, solving power flow, and so on. And we'll just go through this. Okay. All right, but before that, we'll look at something, we'll look at what happens for when we have PV buses. Okay, so the difference between PQ and PV is that when you have a PV bus, the voltage magnitudes are given. Okay, we have voltage magnitudes. Right? So what this does is essentially knocks down the number of unknowns, the number of variables. Because remember for PQ bus, our unknowns are the thetas and the V's, right? We don't know the angle, we don't know the voltage magnitude. But whenever we have a PV bus, what happens is you're given the voltage magnitudes. Okay, we know that what the value is, for example, 1 per unit or 1.05 per unit. So we no longer need to solve. We no longer need to solve this. And what we need to do is basically this reduce the number of equations we have. This basically reduce the number of nonlinear equations because we're already given the solution. We're already given part of the solution. So what happens is before, when everything was PQ bus, we have 2n minus 2 equations here when everything was unknown and when all the V and theta are unknown. But once we're given some of the voltage magnitudes, for example, buses 2 to M are PV buses, are PV. So what we're given is, so that means the voltage magnitudes are given and they're no longer variables. All we do is basically we can directly substitute their values, right? We directly substitute them into the nonlinear equations, and we have a sort of reduced number of equations. Okay, we'll just reduce the number of equations we have, But then once you get a reduced number of equations, we just call Newton-Raphson again. And so nothing really changes in the algorithm. Just for some of the voltage magnitude, you replace them, you replace the variables by the fixed value, because they're given and we don't have to solve them yet. We don't have to solve them anymore. Then we have a smaller system of equations. I will just call Newton-Raphson to solve this smaller system of equations. I just call them. So then, basically, if you look at the procedure, as we just knock down the number of equations we have, and just call Newton-Raphson. So nothing really changes. So we go from system from all PQ bus to system partially PV and PQ bus, because you just substitute the voltage and magnitude with their true values, and then you go. We just continue the process. So any questions? Any questions about this Newton-Raphson? How to run Newton-Raphson? Because you'll be seeing this. So this week's homework is basically getting this to work for a test system. Okay, so let's look at the test system we'll use. So let's take a look at the particular test system we have. Okay. So the test system, the reason we're going to use this test system is we want basically a benchmark for the rest of the class. Okay, we want a benchmark. Okay. And we want to, because we want to solve basically Newton-Raphson for something a little bit larger, let's say 2-3 bus system. However, we don't want you to solve random systems, right? Because it's very hard to check whether it's done correctly or not. So we're going to standardize this, and I'm going to give you basically data for a test system. And what you do is write basically the solver for this particular test system respect to this particular parameters, the problem data. Okay? So this is a lot of your homework will be associated with this one system. All right, so you can, so I'll post all the data online, of course, but this, we're just gonna walk through what the system looks like, how many buses it has, what is the procedure for doing this, and get a feeling of the system you'll be seeing again and again, okay? So on the slide, so what I said is, you're encouraged basically to write your program in Python. So we're gonna encourage you to write your program in Python. Because one, that's open source, we don't have to deal with a lot of the version issues. For example, use MATLAB, then for different versions, depending when you got it, we may run differently. And nowadays, Pythons were, very popular out there. So I'm gonna encourage to use Python if you can. Now, is there anybody who have never seen Python before and really prefer not to use it? So you have never seen Python, you don't know what it is, you don't know how to install it, you don't know how this thing works, and you really just want to use something like MATLAB. Right. Is there anybody who's in that situation? We can make it work in that situation, but it'll be a little bit harder. Okay, so if everybody has at least seen Python or know a little bit about it, then we're going to encourage you to Python. Okay, it just makes grading easier, makes the TA can debug your code easier, this kind of thing. Okay, and we're not going to use all that much from Python. You don't need to install any fancy packages. This is not, you don't need something like TensorFlow, anything like that. Right? You basically just need the basic linear algebra package, and we're going to write code. This, we're going to just write a loop with a matrix inversion. Okay? So it's not you don't need to go very in depth of it, but it's good to use this language, right? So at least for your career, it'll be a little bit better than just sticking with MATLAB for everything. Okay. So the test system is basically a 12-bus system. Okay, so I'll show you the diagram a little bit later, but it's just a 12-bus system. Okay, so let's say if you want to skip through ahead, it's basically this system. It's a 12-bus system with a 5 generators, I think, yeah, with 5 generators, 7 loads. So we're going to try to figure out how do we solve power flow for this. We're going to figure out how to solve power flow for this 12 bus system. Right? So we require, can you write basically a algorithm that has to do with matrices, right? So can you deal with matrices in your algorithm? So this is the topology of the system we'll work with. So I'll give you all the line parameter data and so on, but that's our test system. And what we'll do is we'll study the following. We'll say one is just the basics of the solving nonlinear equations. Can you take the system data? Can you build a Y matrix out of it? Can you build a Jacobian matrix out of it? Can you invert the Jacobian matrix? Right? Okay. We'll try different starting points. Okay, we'll try different starting points. We'll try, starting from a flat start. Does it work? We'll try, what if you don't start from a flat start? What if you start with a random initialization? Does it work? Right. So by playing around with these, we'll give you a little bit more feeling of when do things go right, when do things go wrong. Okay, that's what we do from this test system. And for these people, for the people who's especially interested in algorithms for solving nonlinear equations, there's a bunch of different algorithms out there. Newton-Raphson is one of them, but it's not the only one. Okay, so if some are interested in different types of algorithms, this is a benchmark where you can compare the performance of different algorithms. Okay, this is where you can compare them. Right, so again, we're going to use linear equation as a building block, right? This is where we can assume you can do Jacobians. You can do Jacobians. So by the solution, what we mean by the solution is the following, right? So this is solving the power flow equation for this test system is fairly close to the process of what will happen if you're sitting inside the control center. So you're sitting inside the control center, what you have is you have the system topology up on a big screen. You press a button, say solve power flow, and you get a solution. What we're doing, we're going to try to simulate this process using this fairly simple test system. So when we say solve the equations, what we mean is at the end of the day, we should get the voltage magnitude and angles at each of the bus. Okay, we should get, this is the solution, the state of the system. Then we're going to look at, you should compute the active and reactive power produced by the generator. Well, then again, you look at as, the line flow in each of the transmission lines. We're going to look at, do you violate any of the operating limit, right? How close do you get to the operating limit? Right? And we're going to study that if you, let's say if you have an outage in the system, then what happened to the line flows? How do they change? Okay, so these are the things we're interested in. And this is basically, if you're sitting in a control center, the things you'll be looking, right? The things you'll be looking at on the board. What are the generators' outputs? What are the flows on the lines? Are they close to the limit? Are they far away from the limits? Right? What are the system voltages look like? So this is the things we'll be interested in. And we'll design some cases where things don't go exactly correctly. So we'll try to mess around with the parameters a little bit, and you have trouble converging, basically. Okay, you'll have trouble where Newton-Raphson may not converge, right? Then you'll try to learn how do you look at mismatch. Okay, how do you debug? So how do you debug your code or debug or detect where something is going wrong with the power system by looking at the mismatch in the equations. We'll look at situations when the Newton-Raphson algorithm basically jumps around, right? So if you start with a random initialization point, your initialization point may be very far from the actual solution. We'll look at what happens when the sort of solution jumps around. Okay? When you do the updates, when the updates jumps around, what happens? How do you understand this when they jump around? All right, so So the deliverable, right? So what do you hand in for you when you're doing this homework, right? What do you hand in? So again, you're encouraged to use Python. Okay, you're encouraged to use Python. You can use MATLAB, but so if you're having a lot of trouble using Python, you can use MATLAB. But do let me know. Okay, they'll make grading a little bit more complicated. Because what you hand in for your homework is basically a script. You're gonna hand in a .py file that will just run. Okay, so when Trisha grades this, basically she will open up your file and run it. Okay? So when we run the file, right, the following thing should happen is there should be no bugs. Okay, so when she runs the file, it should actually run. Okay, so that's the first thing, right? So 40% is, does it run? Does the code actually run, without bugs? Okay, whatever and however you wrote it can finish running and output at least a solution. Right? Correct or not, you should output some solution. So this is 40%. Another 40% is, does your code look pretty, right? Is it commented? Is it structured? Can we understand your code? That's another 40%. And the 20% will basically be, so within each question, will be say, write the code and talk about the things you observed. So 20% will be you talking about the things you observe when you're running the code. Right? So that's the breakdown of this for programming questions. Okay, so we won't be having, 6 or 7 questions for homework. We'll be having a few. Right? And one of them be a sort of long programming, will be a programming question. Can you get your code to work? And one thing is, there are a lot of packages already solving power flow in Python, and definitely a lot in MATLAB. You cannot just say I'm calling a package, right? So that's obvious, but explicitly stated is don't use existing packages. What you can do, and what you should probably do, is compare your solution against a solution gotten by those packages. You cannot use them directly, but it's a good sanity check. Yeah, it's a good sanity check for you. You can figure out how one of them works. You can definitely use that as a sanity check. All right, so that's what you should be doing. And it's okay if you compare against each other. Right, so once we're done the program, you can ask other people to debug for you or take a look at your code and tell you what's wrong with it, or compare solutions to get, with somebody else. That's fine. The thing is, don't just copy paste the script, right? Don't just go and take somebody else's code and copy paste it. Because it's fairly easy to figure out whether you copy paste your code or not. Where, there are softwares that are very good at checking whether the codes, the scripts are copy paste from each other, or you just went in and made, small modifications. You just, name variables differently. Those are fairly easy to figure out. Okay, so don't copy paste them. Okay? And you'll be basically working with, this is the topology of system you'll be working with. Any questions with this? With this programming, with what you expect to do, with writing in Python, this kind of thing? Any questions, issues? Okay, so if not, then starting from Wednesday, you'll be seeing homework questions like this, right? So in your mind, what the question looks like is basically the standard question will be solve power flow on the system. Right? I will give you P and Q, and can you solve power flow? Yeah, and then you should be prepared to discuss how many steps did it take to converge. Right? What happens if you change the different starting point? Okay, so these are the things we'll be asking. Right? So the data will be posted, wouldn't be, here just be posted in a spreadsheet, right? So this is just a feeling of what the data looks like. You're given P and Q at each bus, is how much you consume. You're given you're giving the active power produced by the generators. The generators are PV bus. You're given the voltage at the generator terminals. So these are the voltages, those are fixed. The lines are given to you. There's some maximum flow values. In this case, right now we're not going to care too much about the maximum line flow values, but here are just P and Q values in per unit for you. So, right, and we're going to basically solve power flow and check. We're going to solve power flow and check whether the line flows are under their limit. And check are the voltages okay, right? For the low bus, are they close to 1 per unit? Are they far away from 1 per unit? Then we're going to look at contingencies. For example, what happens if I wiped out one of the generators, right? What if I wipe out one of the lines? What happens to the solution? Okay, so for example, if I go on and take out this line, what happens to it? What happens to your solution? Can you still solve the power flow equations, or is the solution infeasible? Do you violate some line flow constraints, right? So these are the things we want to take a look at. So when you're writing your code, okay, you will run into bugs, okay? You have a lot of bugs. Getting power flow to work is a lot harder than what you may imagine. Just because the sheer number of sine and cosines, and just because the derivative of sine and cosine are also sine and cosines, so you run into bugs, right? Everybody, has bugs when they start. Even when you're a grad student, even for now, when I write a program, I run into bugs, right? So you have bugs, right? So you be prepared to debug your program, right? You should. These are just basic, programming practices, good practices, right? So test while you go, document everything, save working copies, right? So every year somebody comes in and say, oh yeah, my program worked yesterday, but I don't know what I changed and crashed today. That's not something we can grade. Okay, we can only grade with the version you submit to us, right? So make copies, have good names for functions and variables, comment your code so we can read it. And right, so use good designs. So these are sort of common practices in coding. Right, so we'll give you the data and the data will be posted. You can figure out how to build the Jacobian matrix. And this is, right, so not much to say beyond that. Right? And do use the TA and do use each other as good resources for writing code. Okay, have other people look at your code, have other people try to debug for you, compare solutions that you get, right? So this is, don't think, oh, it's programming, I'm just inverting a matrix, I can get to work, and wait until, for example, Wednesday afternoon to start doing this. Right? This will take you some time. You basically run into bugs. Everybody runs into bugs here. Right? You have to write the Jacobian matrix, you have to write the y-admittance matrix. And it's probably there's a sign error somewhere in there and it just messes up the entire solution. So it takes some time. Right? It takes some time to be careful with this. Oh, so it'll be 1 week, right? So we'll go with the normal schedule. So it'll be posted on Wednesday, due next Wednesday. Just your homework will be shorter. It'll be like 1 question or 2 questions. Where one is this kind of programming question. So that's what we expected. And we'll keep building on this, right? As we go on in the course. For example, later, the rest of the lecture today, we'll be looking at, if you solve power flow, what if things don't go right, right? What do you change? Right? So we'll keep building on this test system. So it's not like, write solve power flow and this is the end. We'll say, okay, now let's increase all the load by 15%. Okay, let's see what happens. Okay, let's take out this line and see what happens. Let's adding a line and see what happens. And so we keep doing small modifications to this test system. But this week's homework is just can you get it to work? Right, just checking, can you build the Y matrix? Can you build a J matrix? Other questions for this? Right. And once you get to working, for example, when final comes along, we can ask, some this type of question on the final, right? We can say, look, we've been working with this test system. Now let's say I remove a load, what happens? Or I double the load at these 2 buses, what happens? Or I eliminate a generator. So see, these are the questions we can all ask. Okay, so this test system, Wednesday, the new homework, you'll be basically working with it. Okay, so if you don't have Python installed, I highly recommend getting that installed. If you can only use MATLAB, then let me know. Okay, let me know. Because it'll make the grading a little bit different if you can only use MATLAB. Okay, right. So if no questions with this, we'll go to the next topic, basically. Right, so up until now, what we've been doing is just solving power flow, and the equation is, you get what you get. Right? You just get what you get. Now we're going to look at, okay, let's say you solve power flow. And how do you interpret the result? How do you understand the result? Okay, how do you interpret this? So this is a topic called power flow control. Okay, power flow control is to say, I solved it, right? I solved it. But what if the flow is too much, or what if the voltage is not correct? What do I do? Okay, right. So solving power flow in power system is never the the end of the story, right? So it's the first part of the story. It's figuring out the state of the system and figuring out what to do, right? Figuring out how to solve the rest of the equations. For example, power flow control is basically getting intuitive understanding of things like this, right? I have a generator, I'm sending some power to a load. Right? I want to understand, how does the, let's say, changes in load influence the changes in the line flow? How does changes in load influence the changes in voltage? Right? So these are the things we want to understand. We want an intuitive understanding of, let's say, I have too much active power flow. Okay, I have too much active power flow in the load. Then is it because the real part of the load is too high, or is it because reactive part is too high? This kind of understanding, we want to get to it. Okay. So this is our goal of power flow controls. It's looking at power flow equations and getting some relationships between them. So for example, let's look at this, right? Let's say I have a voltage, basically, at the sending end. So let's say we're going to assume the sending end is always at angle 0. I'm sending that through a short transmission line, right? Just R plus JX. We're going to ignore the shunt. Okay, so develop some intuitions, we're going to ignore the shunt in this line. And we have a receiving end voltage. And our goal is to understand, how does everything depend on each other? How does, for example, the receiving end voltage depend on P and Q at the end? Okay, how does depend on P and Q? So we're going to do some calculations, basically. We're going to look at the complex power, S. So we're going to look at the sending, we're going to look at the sending end complex power, which is P plus JQ. And we're going to try to relate P, basically P and Q to voltage magnitudes in this, okay? So S is Vs times I conjugate flowing out of it, right? So what we have is I conjugate. Okay, so we're going to remove current, right? We're going to write everything in terms of voltage and power. So we're going to remove current out of this. So the current conjugate is P plus JQ divided by Vs, right? So Vs is angle 0, so just a real number, right? So we're going to just write Vs here. And then what we have is I, if you remove the conjugate, because P minus JQ, still Vs down here, because Vs is again a real number, you conjugate or not, it doesn't matter. All right, this is our I. So this is one equation for the current, for the complex current. Another equation we can get to for a complex current is basically by looking at Ohm's law, right? By looking at Ohm's law. So we know, so what is VR? VR is Vs minus R plus JX times the current, right? This is also an equation we have for current. Okay. So what we're going to do is we're going to take this equation that relates current to everything. Right, so if we can write this more explicitly as current as Vs minus Vr divided by J plus R plus Jx. Okay, so we're going to basically merge these two equations together because they both is current equal to something. So we're going to substitute current and well, equate those two equations. We do this, and if you do this and do some algebraic manipulation, we get Vr as Vs minus Rp plus Xq over Vs minus J Xp minus Rq over Vs. Okay, so this is the equation we get by relating the two currents by equating the two equations that has to do with currents. Right? If you just equate the two equations, do some algebraic manipulation, you get this as the voltage drop. Okay? This is the voltage. How the receiving end voltage depend on the sending end voltage, right? Where we assume the sending end voltage has angle there. So any questions with this? Any questions with this? Okay, so this is the equations we get. The next slide is just this equation typed out. Okay, just this equation typed out. If you look at this equation right now, it's not obvious why this is useful, right? It's not quite obvious yet why we care about this equation, right? Because what we want to understand, so this here has this, so here we have as VR in rectangular coordinates. Okay. Right, this is rectangular coordinate representation. But when we think about voltage in power system, often we're going to think about VR. What we want is VR in polar coordinates, right? What we want is we want to think about the magnitude and angle of this. We want to think about magnitude and angle, not so much real and reactive parts, right? We don't really, not often when we talk about the real and imaginary part of a voltage, we talk about the voltage, magnitude and angle. Okay, so if I give you a relationship in this sort of rectangular coordinates, can we roughly translate this to a angle and magnitude understanding? Right? If I tell you, I tell you, okay, look, this is what by calculation, I would get this equation, and I tell you the rectangular coordinates. There's some change in the real part, some change in the imaginary part. But can I translate this to understanding angle and magnitude? Right, so let's draw a picture and think of whether we can translate this to angle and magnitude. Okay. So let's think of this as Vs. Okay, right? Since Vs is angle 0, so we're going to draw it this way. Right, this is our Vs. So now let's look at the changes to the real and imaginary part. So basically, right? So what happens if you change the real part? As you move back by a change, right? So the real part of this, we subtract off this real part. We subtract off this real part of voltage. So what this is basically delta of the real part, right? We're going to subtract out this way. Then we're going to move in this direction. We're going to subtract off this imaginary part. So what we move is we're going to move this way. This is the change in the imaginary part. And what we have is we have a new vector, and this is VR. This is my new vector VR. So if you look at this picture, right? You look at this picture. Does change in real part change the angle? right? Does this delta in the real part, does this change the angle of the vector? Does
No.
the angle of the vector? No, right? So the real part, changing real part, has very little to do with the angle change, right? So you look at this angle, this change is mostly from change in the imaginary part. Okay? Mostly from the change in the imaginary part. Because the real part just pushes back and the angle stays the same. But we have an angle difference because we're changing the imaginary part of the voltage. Okay? We're changing the imaginary part of the voltage. Right? So this is the intuition, right? This is what intuition we have. Then if you look at the magnitude, then which contribute to the changes in magnitude? Does the imaginary part contribute more to the changing voltage magnitude, or does the changing real part contribute more to changing the voltage magnitude? Right, so the imaginary part basically turns this vector, right? All it does is turning this vector. Okay, it's turning this vector. Then what happens to the magnitude? As most of the magnitude change come from the changing real part. Okay, so this is most of the change in magnitude. Okay, so most of the changing voltage magnitude comes from the change in the real part of the voltage vector. Okay, so when we get a new vector in VR, what we're doing is we're changing the real and imaginary part, and turns out the real part contribute a lot to the changing magnitude, not so much to the changing angle, and the changing the imaginary part contribute a lot to the changing angle, but not so much to the not so much to the magnitude of the voltage. Okay. So there's actually a lot of intuition in power system engineering in power flow comes from this observation, basically. To relate a rectangular coordinate to a polar coordinate, at the very high level you can think of the magnitude depends on the change in the real part, and the angle depends on the change in the imaginary part. Okay, so this is what we have. This is the picture we should have in mind. Okay. So, right, so this is again just a type L version. Okay. So what we have is this thing to remember, this is important sentence to remember. Okay. The magnitude is caused by the changing real part. The angle is caused by the changing in the imaginary part. This is a thing to remember. Right. So again, to draw this again is to say that we have two vectors. This angle is mostly due to delta V M, and this changing magnitude is mostly delta V real. Okay, so they contribute different parts. So I guess let's take a break now, I guess, because after this, we're going to make more simplifications and we're going to get more explicit relationships. Okay, right? Our goal is to understand. So this is not quite there yet. Our goal is we want to understand is how does active and reactive power relate to voltage and angle. Okay, so let's take our break now, and then when we come back, we'll get those explicit equations. We'll get how P and Q relates to theta and V. Okay, so let's come back at the 10:26, and we'll look at those equations.
Good morning, Professor.
Yeah.
I was wondering, when we're going to be using Python, I've been using this Google Collaboratory Notebook in one of my other classes, and my understanding is it essentially runs Python. Can I use that?
Yeah, you can use that. Yeah.
Okay.
So as long as it's open source enough that when we grade it, we just have to click run. Right. That's the thing we want.
Yeah.
We don't want to do any version control issues. So in the past we use MATLAB, but MATLAB is always a version issue.
Okay.
If we're using 2020, you're using 2020, 2019, and that's a problem. But if you use any of those online notebooks, it's fine. You can use those.
Okay, sweet, thank you.
Professor, just a quick question. On the for the delta V real, does that include the VS minus the RP plus XQ over VS, or is it just the negative RP plus XQ over VS? Just that part, so without the VS. I think the microphone is muted.
All right, yeah. So we're gonna refer everything to the VS. Yeah, just a changing VS. Right. When I think of VS as a reference, yeah.
Okay, thank you.
All right, okay, so let's get back to this. All right, so if you look at the changing the real part and the changing the measuring part, right? The equations are still not super friendly to work with, right? This has, R, P, X, Q in all of them, right? So one is R times P, one is X times P, for example. So it still looks, fairly complicated equations, not too clear what the role of P and Q plays in here, okay? So we're another approximation we're gonna make, okay? So if you look at these two equations, has both R and X inside in it. Which one do you think is larger, the value of R or X? Just from, for example, the homework questions you have seen. Right? Is R larger or X larger for normal transmission lines? Right? X is larger. Right? Lines are mostly inductive. Okay? So the assumption we're gonna make, which make things very simple, is we're gonna say that X is much larger than R. So we say X is much larger than R. What happens is we're going to basically not care about the R terms in these equations. So what does this give us? It gives us that the changes in the real part, this is equal to, if we ignore the R term, X over XS times Q. And changing the imaginary part, this is X over VS times P. Okay, so these are the equations we get. And this equation are actually quite important in power systems. Because these are quite important because they give us the following statement that you will hear very often. What this tells us is basically the voltage magnitude depends on Q, right? Because we said the changes in the real part changes the voltage magnitude. So very often you'll see statement like, oh, the voltage magnitude depends mostly on Q. And this is the reason from this equation. Because if you look at this equation, P goes away for the first equation and only Q remains, right? So you can almost view this as, as a linear relationship with respect to Q. And the coefficient is X over VS. And if you look at this one, this is basically angle depends on P, right? Depends on active power. Because the changing imaginary part basically rotates the vector, so that causes the changing angle. And if you make the assumption that X is much larger than R, then only P impacts the changing the imaginary part. Okay, so then consequently, P impacts theta, or P impacts angle. Okay, so angle only depends on P. So this actually is a quite nice decoupling in the power system, because the magnitude depends on the reactive power, and the changes in angle depend on the active power. Okay, and this is often the first order approximation we'll use when we think about system operations. Right, we'll say, okay, is the voltage okay? Right, the voltage depends on the reactive power. Is the angle okay? The angle depends on the active power. Right, so this is sort of decouples what the voltage and angle respect to active and reactive power. Okay, so this is important approximation we'll use. All right, so this is important to remember. A lot of the intuition when you talk to power engineers come basically from this equation, right? From these two equations. There's multiple ways to get to this equation, right? There are multiple ways to get to it, but they all come to the similar conclusion. You can do more formal analysis about explicitly on angle and the voltage magnitude. You get, the same equations left over. Okay. Any questions about these two equations? Okay, so these are two equations that we have. So they are from the assumption, right? Basically, x is much larger than r. Okay, so this is our Rx ratio or x to r ratio we have. So let's look at it. So for transmission networks, meaning high voltage networks, what do you think the x to r ratio is? Ballpark wise, anybody have a guess? Like it's big, right? So we need to understand how big is big, right? So numerically, the big means, so here for transmission network, this is roughly 10 or higher. Okay, so x is 10 times larger than r, meaning it's much more an inductor than a resistor. Okay, so it's not a bad assumption to ignore r. Okay, so for high voltage transmission lines, we just ignore r because x is fairly large. Okay. For distribution, this means a low voltage network, right, inside the city and so on. What do you think this is? Is it smaller or larger than before? All right, so for a high voltage network, this ratio is 10. For a low voltage network, what do you think this ratio is? It is smaller, and often it's quite a bit smaller. This is around 2, or you see something like 1, or sometimes x, r is larger than x. You do see these things happen. Okay, you do see this kind of things. Okay, so basically, this says that for this, x larger than r is okay. Okay, so if it's 10 times difference, an order of magnitude difference, then our intuition is fairly good. Okay, for this, x larger than r is not okay, and you design wrong algorithms, or you have wrong intuitions about the network if you just assume a decoupling between voltage and angle based on active and reactive power. Okay. Right. So in this class, we're going to mostly focus on the first part. So we're going to look at the transmission network. So all the intuition we have is fine. You can think of reactive power driving voltage, active power driving angle. That's an okay intuition. But when you come to a distribution network, for example, Seattle City Light network, then it's not this simple anymore. Okay, it's not this simple. Right? Anybody have a reason why for distribution network is less? Why the resistance higher for distribution networks? Right? What's different with transmission line? Right? Why is it why is ratio 10 in one case and not any other case ratio is 1 or 2?
Would it be because they're delivering the same amount of power, but lower voltage means higher current, and current contributes to more real power loss in terms of
a
the
little bit. Current heats a line. Basically, current contributes to heating, and once you heat it up, it's more resistive. That's one reason. Another reason for more from the physical design is the lines are not as good as a conductor as transmission. Right? For distribution, basically you have so much lines, and you want to put them underground, and you don't want to spend. They're carrying actually less power, right? Because once the line gets into a city, and each load basically absorbs some power, so by the end, you're not carrying as much power. So you basically have the chest as thinner lines, which is basically what you have. Right? The lines are not as big as before, and not as bundled as before. They're underground, which they're packed much closer to each other. So all of this comes together to make the XR ratio not as high as before. Okay, so it's just different lines. They're physically just different lines. Okay? So they're copper lines, for example. Right? So it's important to keep in mind, right? This intuition may not work so well if you go on to work for City Light or Puget Sound Energy. Right? However, if you go on to work for a system operator, for example, California system operator, this intuitions work perfectly fine. Just something to keep in mind, right? When they break down and when they work. All right, so this just formalizes this as, so the red box is important, red box is important, and tells us to remember that reactive power contributes to voltage drop. Active power contributes to angle difference. Okay, so this is the key factor to remember. Right? So basically, if you summarize this as a phase angle difference makes active power flow, basically, right? So active power only flows. So mostly, so this is, so we guess the converse or the inverse relationship. Right? So this is equation tells us theta depends mostly on P. The converse is true. Basically, P depends on theta. Okay, so P depends on mostly on theta. So when you have a lot of active power flow, it's actually driven by the angle difference. Okay. So one thing that people may not realize is when you learn circuits from before, what drives current, what drives power is a difference in voltage magnitude, right? In voltage. When you have a simple circuit, so you have a battery, with a resistor, with a light bulb, as basically the changing voltage drives the power flow. But when you look at transmission lines, we say that almost all the voltages are roughly at the same level, right? So we say, oh, the voltage, as 100 kV, or we have different transmission voltage levels. The reason we can have similar voltage levels but still drives a lot of power flow is because active power really depends on the angle, okay? Not on the voltage difference, but really on the angle, okay? On the angle of the buses. And this is something to remember, that it's not the magnitude. Magnitude doesn't matter. It's the angle that drives power flow. So when you look at the two buses, when you think of potential difference, when you think of the difference in voltage potential for a transmission network, the difference in potential actually comes from the difference in angle. And that drives power flow. And that drives this active power flow. Okay, so right, and similarly, this is similar. This is Q mostly depends on the voltage. This is magnitude. Right, so the reactive power is mostly driven by the voltage and magnitude, whereas the angles don't contribute very much to it. Okay? But the angles don't contribute very much to it. All right, so okay. So that's why we can very possibly have. Okay, it's very reasonable to have that P and Q flow in different directions. Okay, nothing in the equation says that the P and Q has to be in the same direction. You can very well have reactive power flowing from the load to the generator. That's possible. So this, for example, this can happen as, for example, right, I attach a capacitor to the load. I can drive reactive power flow the other way. I can drive reactive power flow the other way. So if this happens, which one of these have a higher voltage magnitude? Right, so suppose this have VR, right? So if this happens, if reactive power flows the other way, VR can very likely have a higher voltage magnitude than VS, right? So if you look at our equations, we have is the change in the real part as X over VS Q, but here Q is negative, right? Because the generator is receiving reactive power, the Q is negative. So if you look at our diagram, this is basically VS, what happens is we add a part, right? So negative VRE, this is actually extends the magnitude of our vector, extend our vector. Then we do a change in the imaginary part. So if you look at this, we have VR. So it's very possible that VR is larger than VS. It happens. Okay? It can happen. And in practice, it often happens if you happen to have a capacitor at the end of the law. So that's why, you know, for example, in the midterm, when you see a pi model with capacitors, you can raise the voltage. It's not, there's nothing wrong with it. It doesn't counter our intuition, right? And P can still flow from the generator to the load, while Q can flow the other way. So this is all very possible. All right, so any questions about this kind of situation? Okay, so this kind of, you know, this happens. You know, if it happens, don't be alarmed. You can have voltage differences.
Professor, I had a question.
Sure.
So before, were we considering like a positive delta V real to be
right?
Like you're subtracting the positive from the
Yeah.
VS?
So right. So the convention is V real. We have a negative V real, and we're going to move backwards this way, right? So if you look at this picture, so if you look at the equation we had from the beginning, we have negative signs just built into the equation.
Okay.
So we're going to think of subtract V real, subtract V imaginary, right? So here we're still subtracting, but we have a sign difference because Q is less than 0. So this is extending, making it sort of larger, the magnitude larger.
Okay, thank you.
All right, thanks. Okay, so this can happen, right? This happens, and you know, sometimes we want it to happen. Sometimes we want to raise the voltage. Okay, so another thing to remember for the losses is, right? So often you hear people talk about losses. Most of the losses in our system is actually reactive power loss, right? So reactive power loss is often larger, much larger than active power loss. Okay, right? Because X is much larger than R. X is much larger than R, so they are reactive. You just happen to lose more reactive power in the system. Okay. Another thing to remember is reactive power loss is not energy. You cannot measure in joules, for example. It does not have a unit of joules. Okay, reactive power loss is basically an oscillation in the inductor you have. Okay, this comes physically just energy oscillating in your inductor. Okay, so it's not actually, you're not losing work, right? You're not losing joules in that, right? So that's another thing to remember, right? When you do power engineering, when most people think of loss, they're gonna think of active power loss, right? You know, you may even hear, you know, people working in policy or in the market side saying, oh, you know, the losses in the system, which they mean active loss, people try to reduce active power loss. For transmission networks, reducing active power loss in the transmission lines is not a huge deal. It's not all that important. If you can, most of the time, if you're an engineer, most of the time you're fighting against reactive power loss because X is so much larger than R. Because X is so much larger than R. Okay. So one thing we can think of is, what is so bad if you're losing a lot of reactive power? Right? Why does sometimes you want to basically do some reactive power compensation? Right? So since reactive power is not energy, right? In one sense, you're not wasting power when you have reactive power loss, right? We're not wasting joules, and none of your generation is going to right? Your generation is not going to reactive power loss, right? You're not losing money that way. But often we want to fight against reactive power loss, or we have different ways to deal with it. So can you think of some drawbacks? Let's say I have a system, I'm losing a lot of reactive power in a transmission line. What is a drawback?
Wouldn't it mean that you have higher currents to supply the same amount of power you otherwise would, right?
Right. So
stuff.
yeah. So what happens is basically you're taking up a lot of room in my transmission line, right? So when you have a transmission line, basically, if you think of this as the transmission line capacity, right? Think of this transmission line capacity. There's some fixed capacity. So if you have a lot of reactive power, if all this is taken up by reactive power, then you don't have as much as room for active power. Okay, so this is sort of the mental picture we can have. I have some line, the line flows some current, right? So now there's some limit to that. And if I'm doing a lot of sloshing back and forth on reactive power, it's not losing energy, but it's taking up my room, my transmission line, right? So I'm using the system less efficiently because I want to transmit active power. I can't get it there. There's a lot of my line is thinking about reactive power. Okay, so that's why often you add capacitor just to damp this out, right? Try to leave a lot of room for active power transmission. Okay? And so a lot of engineering, capacitors, stock comms, big equipment is fighting against this. Okay, so again, if you remember a picture from before, is most of the substation is stack comms basically, right? If you ever go by them and people ask you what do those do, they're basically has nothing to do with the active power loss, right? It's not making the system more efficient in that sense, but it is making more system efficient in the sense that you're basically having room in the transmission line. Okay? You're basically opening up room for transmission of active power. Right? That's why reactive power loss is still important, even though it's not energy. Right? We're not talking about energy, but we want to clear some room for active power transmission. Right? So that's for reactive power loss. Okay. So rest of the class is basically we're going to look at some examples. Of if you use power flow, right? How do you use it? And what do you do if you're not happy with the result of your power flow? Okay. So the application of power flow is basically you have a system, you press a button, it solves power flow for you. And you look at the voltage bus magnitude, you look at the angle, look at line flows. And you think of, am I happy with the solution I get? If I'm not happy, what do I do, right? What do I change in the system? So power flow is used in all kinds of situations. For one situation it's used is, for example, in planning, okay? In power system planning. So power system planning happens over, a few months to a few decades. Sometimes we plan, 10, 20 years ahead of time. And what you do is you basically forecast all the load in all your buses. You look at, am I building new power plants? And you think about it for the projected load growth or load changes versus the project changes in generation. Is the system still okay? Right? Is the voltage still okay? Is the power flow still okay? Right? Do I need to do something more? Do I need to build more generation? These are the questions you look at. So for example, let's say we're solving a power system planning problem. So I have some load and I have some generation. And during the planning process, I figured out the flows are too high. Okay, meaning that this is either higher than my limits on my transmission lines, or that they're getting uncomfortably close to the limits of my transmission lines. Okay, so you get this, you get the you will figure out the flows are too high by solving the power flow equation. Okay, that's what solving the power flow equation will tell you. Right? What we need to think about is if it's too high, what can you do about it? right? Let's say we are, we are system engineers and you're doing planning. So what do you do if you figure out your flows are too high? Any suggestions of what you can do? Let's say you're working for BPA and you project, Seattle will have some low growth. And for the current generators we have, our transmission line really cannot handle this. Right, so then you're basically, your boss asking you, okay, what do we want to do about the situation? Right, any solutions you can think of if the line flows are too high?
Professor, you mean
Yeah,
the power is too high or the voltage too high?
The power, the flow. The flow means power, right? The line flow means the flow on the line.
The real power is too
high. No, let's say the current is too high. That's a reactive power also matters, right? As we just said. Line flow, a lot of taken up by reactive power. Right? So both of them contribute to current. So like you can think of the apparent power, and I think of this as S. S is too high. Okay, so let's say your S is too high. So what do you do when your apparent power or current is too high? Because your lines are not good enough to handle it.
Shut down plants, if that's an option, or
no, shut down plants is not good, right?
Probably not.
You still want to
yeah.
deliver power, yeah. So if you tell your boss, "Oh, shut down plants," that's not so. Don't say that. Don't say that to your boss. Shut down plants.
Could you maybe adjust the voltage to bring the power factor closer to unity?
Right. So that's a good suggestion, both in chat and what was just said, right? So one is you can raise the voltage, right? So. Okay, maybe not have so much reactive power flow in here, right? Maybe, try to cancel some of the reactive power flow by making voltage closer to each other. Raising the voltage is one solution, right? Another solution is just to, upgrade to a higher voltage level. Right, so if you're operating, let's say, at the 65 kV before, you may want to go to 132 kV. Right, so that you may want to just raise the voltage for everything, but that will reduce a little bit less current flow. Okay, so other solutions. One's raising voltage. What other solution do we have?
Add another transmission line to distribute the current.
Right, so add another transmission line. So one is you can add transmission line. Right, add transmission line. Right, so that's what you can do. And another thing is you can reduce the load. This is more on the energy efficiency. Or as I say, demand response. Okay, so again, it's actually good to look at a practical example. Some of you may be working on this. If we go to status line, okay, so if we draw a picture of, let's say, this is our, this is the UW campus. Okay, so we're facing this is actually a problem we have, So this is our campus. Does anybody know where our substation is? Right, so we're getting power, but the power we have to do a transformer. We have to basically do a down conversion for voltage. Anybody know where that substation is? That powers most of the university.
I think it's next to the 8th Avenue. It's on the west of the UW campus. Next to
right, so west of UW campus is actually under I-5. So you ever driven by I-5, it's basically close to where I-5 passes the bridge. Okay, so we're basically, what we have is we have a primary substation. So we used to offer tours to the substation every year. This year, so for obvious reasons, we're not doing it, but we'll probably restart, once things are better when we can, have groups to go out at one time. So we offer tours to a substation, and you can go in and look at it. This is basically under the bridge. And what happens is this comes down to somewhere around, this is 15th Street, 15th Avenue. There's another substation, and this goes into the UW campus. So almost every building on the UW campus is fed in this way. So this is the transmission line, comes into the substation by I-5. This goes under, whatever, I forgot the exact name of the crossroad, 42 or 43rd, 42nd or 43rd, and comes on 15, okay, in UW campus. So if you see the generators by the trail, those are only for the hospitals, because those do not power other academic buildings. Because those are only for the hospital. So our power situation is basically like this. Okay? So if you look at our plan for growth, for load growth, for example, we're going to build a lot of new buildings. So we're going to have a lot of load growth here. Okay? We're going to have a lot of load growth here in our campus. If you look at the campus master plan, we're planning a lot of additional buildings and additional square footage. The problem is, this is limited. This is sort of flow limited. We cannot flow more power through this lines. Okay, we cannot flow more power through this lines. So if you look at our solution, right, we say, oh, we can upgrade the voltage. We can step up the voltage. This substation, this is by where the campus police headquarters is actually. It's not far from there. This is space limited. Meaning, cannot put in a bigger transformer, okay? So this limits the transformer size. Cannot be too big. Okay, so if you cannot have a big transformer, you cannot have high voltage conversion. Okay, so the bigger the higher the voltage, or the bigger the transformer you need to step it down. Right? Just sort of physical size of transformer. Okay. So we're facing a situation where the load, we're trying to grow the load, we're trying to do campus extension. We cannot step up the voltage because there's so much, just the building is so big to house the transformer. Okay? It's not going to get bigger. The lines are flow limited. Okay, so what are some of the possible solutions you can think of? This is actually real. So if you work for the campus, you spend a lot of time thinking about this. And you work for City Light, you spend time thinking about this. So what can you do? Right, what can you do? Can we add the transmission lines?
No, it's too expensive.
It's actually not too expensive. We cannot add transmission line because we run out of room, actually. So if you know where that is, it's basically again by student dorms. And then nobody will give you the permission to put overhead lines by student dorms. Okay, so Seattle will have windstorms. And if what happens in windstorm, your lines fall down, and if that touches the student dorm, right, so not a good situation. So you have to go underground. But we have no more room underground, as there's things underground, and where that room is all tapped out. So we can't add lines. We can't step out the voltage because we don't have no room. Right? So yeah. So any suggestion on what we do? What possibly can you do?
Can we add the shunt capacitors?
Only happens to some extent. The shunt capacitor, what happens is you can reduce the voltage difference, but cannot step you up, say, from 65 kV to 100 kV. That you can do with shunt capacitor. Right? So basically, this is an interesting question. Right? This is actually where research is quite close to home, because there's no off-the-shelf things you can buy. You go to companies and say, oh, I have this situation, deal with it. Actually, they don't have a solution that has been tried. Right? We don't have that. So what we do is, as said in chat, is you can do storage. right? You can put storage on campus. Has its own challenges, but we may have to do that. We can do like demand response, for example. We may have to do demand response. We can do solar. Okay, so these are, we can do building efficiency on campus. These are actually all things being talked about. Okay, and we have, we have heard from companies that propose following situation that, we can do superconducting lines. That's one thing you can do. Once you get to superconductor, you have no heat, and that's being actually considered. Believe it or not, we may have very fancy superconducting technology just to get power to our campus. We have superconducting lines. We have all sort of new and weird technology being talked about. Right? I sit in some of those meetings, try to look at whether they're feasible or not. So, maybe in 5-10 years, our campus will be very advanced in power transmission. Not because we want to be, it's because just when somebody designed this infrastructure, they never thought we're going to grow past our peak or something, and then now we are past our peak. So we're just forced to do it, right? So yeah, so when you think about this kind of situation, when you look at homework questions, you think these are academic, they're actually not. Okay, so these are, hundreds of millions of dollars on the table, and we're looking at different technology solutions. And often it's not clear what the solutions are. For example, I heard pitched by superconducting folks. They asked them, have you tried this anywhere? And say, no, we think you're a good place to try this. Try superconducting. So you have interesting things. Right? You think of interesting solutions, there's also a way to apply them. Right? Okay. So this is one example to keep in mind. Okay, one example to keep in mind. Definitely, things are happening close to home. Okay. Any questions about this example of our campus situation? Right, so yeah, so I encourage you to get involved. Actually, be interested in this and interested in this kind of questions. One group to get involved on campus is UW Solar. Right, it was a student organization, but it's now getting to a lot more than just solar. They're getting to think about this sort of infrastructure questions. And in the future, we're going to see this more and more. Really, this kind of situation will pop up more and more. Because if you look at the low growth, let's say in the US, what do you think the low growth is for the country year to year? How much is the low growing year to year? Any guesses? Or even Seattle, you look at the city like Seattle, how much is the load actually growing? Right, so if you look at as a country or big cities, the load is essentially flat, or sometimes even trending down a little bit. Okay, the load is sometimes is almost flat for the country, right? It's like point some percentage before COVID, so after COVID, may even go down a little bit. Right, so and you look at Seattle, Seattle is almost flat. It's 1% or not even. But what is happening is even though the aggregate load is very flat, what happens is you have concentrated load in different pockets. For example, UW is load grow quite a bit. South Lake Union, the load grow quite a bit. Downtown, the load is growing. So before we were doing sort of planning, all we did was looking at for a city, what's the load growth? Do I need a new generator? Do I need a bigger transmission line? Now it's becoming very localized, right? For this to block, what do I do? And when you get to this kind of question, you're always concerned by space. I can't put in new transmission lines. I can't put in new substations. Then it becomes, the different technologies towards the end of the grid, right? Doing demand response, doing storage, doing fancy power electronics, all become a lot more, or we're forced to use those kind of solutions. So it's an interesting time in power engineering. It's actually, a lot more interesting now than I would say 10 years ago, when all the answer is, putting a capacitor, putting a new transmission line. Now this is that we forced to think about storage, solar, power electronics convergence, solid state stuff. It's a lot more interesting, and you'll see more things like this as we go on. Right, both driven by climate change when you have to turn off transmission lines, and just load is growing very unevenly in different parts of the country. Okay? So these are just interesting things we have. Right, so this is something to keep in mind, back in your mind, right? So when we say things on paper, it's like, oh, add a capacitor, sometimes that's just not going to happen for different reasons, and you need new technologies, right? So for example, if you see voltages are too low, the common answer is just to add a capacitor. Right? So this is everything we said before, but we can add a capacitor right here to boost the voltage, right? Whether that's possible or not, depending on your exact situation, but often we want to add a capacitor here. Right, you may have, the load are too high. Here you basically add an inductor. Add inductor, so you have a switching inductor to the load. Right? So all this is what you can do. And for example, we see a lot of wind generation. We look at this kind of situations. We'll be adding sort of static, we're adding sort of dynamic inductor or capacitor to the load. All right, so these are things that could happen when you run your planning process, and these are some solutions you think of. Okay. And then you work for a utility, a lot of your time is thinking about this kind of problems. Right? I have a plan changing load. What are the things we can do? How much budget do I have? What are the good technologies? How much space do I have? So a lot of your actual work is thinking about this kind of things. You're running a lot, additional simulation, looking at different products. So these are a lot of your work in a utility. Any questions about this for planning process? Okay, so if you work for a operator, you won't be, you think about something in planning, but often your things will be thinking for hours to a few months. So this is the operation. So when we talk about operation means that we're not going to add new things, okay? So you're not going to add new plans, no more new plans, no more new lines. You have what you have, and you run power flow and try to see what happens. You run power flow. All right, so basically now your control actions are not adding in new things anymore. Okay, there's no more things to add to the system, right? That has finished. So your options are different. Okay, so let's think about if we're doing active power control. So what can you do then to change active power? Let's say again we run power flow. I figure out, hey, there's too much active power flow in a line. What are the different options? What are our options we can do? So if you're operator, you press a button, and on the big board it says warning. This line, is over the flow limit. Then as the operator, what are your options? Okay, so your options are basically the following things that you can do. You can do a redispatch. What does redispatch mean? Okay, what does redispatch mean? Remember our power flow equations. Okay, we have PQ, these are loads. Okay, so you're not going to control the loads. We have PV, these are the generators. Okay, so this P is actually controllable. Okay, this is controllable. So redispatch, meaning changing the values of the generator P. Okay, so the generator, maybe it was generating 100 megawatt. You may want to ask it to generate more or less. Okay, so this is what redispatch means. As my PV buses are the generator buses, right? Those P's can be changed because they're generators. Redispatch meaning recomputing the P for the PV buses. I want to recompute the P. And if I because power flow depends on how much power a generator is generating. So if I recompute the active power being generated, I can actually, change the power flow on the line, right? So this is actually very effective. This is super effective, but this is costly. So why is this costly to me? Let's say I'm an operator, I'm sitting here, and I want to tell a generator to, okay, go change your dispatch, go change your set point. Why may a generator be unhappy about this? Right. So what's stopping me from, changing this dispatch every minute or so? Right. Let's say I'm a operator. I keep telling a generator, oh no, oh it's 100, oh it's 105, oh it's 98. No, I was gonna tell you a new set point every minute. You will get a complaint from the generator. So why might a generator complain? It will just keep telling it change different levels. Okay, so let's imagine if you have a nuclear generator in your system, are you going to tell a nuclear generator to change its power? Right, so inertia, which means that some generators do not like to change. For example, if you have a nuclear generator, your nuclear plant is not going to change its dispatch every hour to hour. Okay, we'll tell you no, I'm not changing my dispatch. If you have a hydro plant, it may not want to change its generation every hour to hour or minute to minute. So basically, what happens is generators have ramp limits. Okay, they're basically how much they can ramp up and down. It's not instantaneous. Okay, right? So if you have, for example, nuclear, this is days or even weeks. Right, yeah, just say days. Okay, nuclear is not going to change its generation very fast. Then you have something like coal. Coal is hours. Okay, coal-fired plant actually to change its output appreciably takes a while. It takes a while because you basically have a boiler, and coal doesn't basically burn all that fast, so it takes a long time. You have gas. This is, let's say, 15 minutes. Gas are faster, but not instantaneous. What is the fastest things that can change is actually power output? For all the generation we have, what can change our power output essentially instantaneously?
Hydro plant.
No, hydro plant are big machines. They're probably similar to coal. They're not going to change instantaneously. Right? To change hydropower output is not easy. Right? Solar. Right? So anything with DC basically. So solar or storage, because they're essentially electronic. Right? Solar has no AC components. Storage has no AC. Right? Where AC basically comes from a electronic conversion. These are milliseconds or microseconds. Okay? So these are instantaneously, essentially, solar and storage to us. Okay? Storage can track a power change almost perfectly if it has enough energy and power. Okay? So when you talk about redispatch, there are some resources in the system you can change very fast. Solar, storage, wind to some extent, gas. Some things you're not going to change very fast at all. For example, nuclear is not going to do anything. If you tell a nuclear, oh, can you reduce your output in next hour? It's like no, right? So it's not going to change its output. Right? So coal, is somewhere intermediate. So when you operate the system, we want to redispatch. You have to keep in mind the time scale you're talking about. Are you talking in a day or are you talking in a minute? You can call different resources differently. Okay, so we'll get more into this once we go sort of later in the course. As how do you online a dynamic fashion change settings? It's not trivial. It's not trivial. Okay. So, and another technology we have is so-called a phase shifter transformer. Okay, so this was used quite a bit before we had a lot of, for example, storage, right? Since coal and nuclear hydro cannot change very fast, we have something called phase changing transformer. So we have 4 minutes. Okay, so we'll do this next time. We'll do phase changing transformer next time. We'll look at basically if you want to install some equipment, right? So in the system, how do you do it? So remember, we want to dynamically change voltage. We have something like StatCom, where we had a dynamic, basically a capacitor where I can vary the rating, vary the capacitance dynamically. Phase changing transformer is something analogous. If you talk about active power flow, is how do you dynamically basically shift the phase in inside transmission line. Okay. So we'll stop here today. We'll look at this next time. Next time we'll look at phase changing transformers. Right, so from now on, again, remember, we'll do a lot more programming. When we're doing the programming and think about planning, the one example you can keep in mind is our own campus, where we are running into issues. So when we're solving a homework problem, we're saying, oh, this line is loaded close to its limit. It's actually a very real situation. Lines are being loaded much closer. Okay, so that's something to keep in mind. Right, so yeah, so I'll see you on Wednesday. There's no questions. All right, thanks, guys.